Okay, because otherwise I might get confused, at least in the first few weeks. Okay, but we'll see how we go with this. I might be able to help more people as you come up as well. Okay, so let's get started if you're ready. So the first thing you need to do is open up your Anaconda and open up the Jupyter notebook. Okay, do you all have access to that? Okay, great. So we see our problem set here. We've got 4 main problems. Let's just have a look at the first one. Okay, now we're asked to create a script that approximates the infinite series of 1 on k squared. Okay, so that should be zeta, the zeta function at 2. And we know that this is meant to be pi squared on 6. So what we want to do is see if we can get a close approximation to that by subtracting pi squared on 6 from an approximated version of the sum. And we hope to get something that's near 0. So I first have mine set at 10. So now let me ask you, do you have the code written out, or do you need to type this? So I need to know. Do you need to type now? Okay, so let me know if I need to slow down a little bit. So I've got the first piece of code here in line 1. Okay, now you might have had that already set at something like 10,000. So obviously, as the number uppercase n increases, the approximation should get better and better. All right, but just to see that this works, I'll change it. Okay, so now I'll have this up to 100 because I previously executed the first 10 summons. And so now I'll do it to 100. And what we'll do first is press shift and enter. Now, if you haven't done any calculation before that, it'll take a little bit of time to start up the kernel. And it'll let you know somewhere, I think up in the top, somewhere in there, I remember that the kernel's initiating. Okay, so it looks like mine finished, but yours might be still running. Now let's have a look at this code a little bit. So we've got n equals 100, so it's putting n in memory. And then we've got a sum with a round bracket around that. And inside that, we have a square bracket, what we're adding together, the 1 on k squared, and then 4k in 1 colon n, so 1 to n. Okay, so that's pretty straightforward. And in fact, a lot like what we did in Mathematica in semester 1. Right, just a slightly different syntax. All right, now remember, because we want to check whether or not this is approximating pi squared on 6, what we do next is we subtract it. But here, Yoni's got a comment, hash \pi and tab gives you pi. All right, so you can just write \pi, lowercase, press the tab button, and that will convert it in front of your very eyes into the Greek letter pi. Okay, so and then once you're comfortable with running this for a small case, you can increase this, say, up to 10,000. I think that should run in a reasonable amount of time. Okay, so now what I get is minus 9.99 times 10 to the minus 5. So you can see that it's getting fairly small. Okay, so how's everyone going? Let me have a look on Zoom here if I can see the chat. So just bear with me while I look around here. Okay, good. All right, so I'll put the chat box down in the bottom right. so I can see what people are saying online. Okay, so Yoni says, can hear you, but with feedback. Thanks, Yoni. So that was Wallace's computer right next to ours. Is it better now? All right, so Wang says, hi Wang, how to type pi in the Jupyter notebook. Okay, Wang, so it's just the \pi and then you press tab and it will convert that for you. So just like what you see here. Now there are a few of these along the way where we've got a hash and then some words. Now a hash is a comment there, which you can keep in line. And I always think it's a good idea to put these comments in because when you write some code, if it might be quite elaborate, like you're building some functions, for example, and you come back a couple weeks later and you forget what those are actually doing. So it's always a good idea to comment your code. Okay, so next, we're going to build a histogram. So to do that, you've got to enter this using plots, right? And that could take a little while to load if you haven't already. And then once you have, the histogram should work. All right, so what we've got here, and so I'm talking about line 3 now, histogram, rand 10,000, label equals false, n bins 50. So let's just talk about what all of that is. So I think that we're getting 10,000 random numbers between 0 and 1. We don't have any labels on our axes. And n bins should be how many rectangles we want, right? Because there could be a number of random numbers that fall in a given range. And so if you had more of these n bins than 50, you would have many, many more rectangles, and you might not like that. So, all right, so let's try this out. Shift enter. Okay, so it's calculating that. It's telling me that the histogram is not defined. Okay, that's probably because I skipped using plots. So I've shut this down since I last used it. We'll have a go at this again. All right, now have a look. There's an asterisk there on the left inside the square bracket in. So it's running loading that cell or loading the plots. So we'll wait for it. Okay, it's taking a little while. And there it's done. Okay, so that should be good. I hope that I can now run a histogram. Let's see, shift enter. And that's running. Okay, hi Molly. So you've got a comment. I'm still having issues opening Jupyter from Julia. It would be great to get a hand with that when you have a moment. And Zhang Bai says, me too. Yeah, well, I had this issue this afternoon, but thanks to Yoni's help, I was able to clear it up. So let's see if I can remember what you all have to do. So you have to get Anaconda running. You have to have one of these IPYNB notebooks on your PC somewhere. So you would open Anaconda. So on my laptop that I'm using here, it's this green thing right here. So I'll just pull it up. Okay, so it looks like this. So to open that, I go here to find Jupyter with a Y. notebook, and you might have a different number down here on the system at home. It starts with a 5, but here it starts with a 6, and then I press launch. Okay, but I've already done that. So that's how to get that to work. All right, now when you're starting that out, you might want to try something really simple, like adding two numbers, 3 and 4, for example. And then when you want to do more sophisticated things, well, you have to go in and install one of the packages. Okay, now in this notebook, we have some hints along the way about how to do that. So for example, I went into Julia and I typed out using pkg semicolon pkg.add that we see right here, and then round bracket quotation plots. Okay, but Yoni tells me that you can do that here in Jupyter, if I remember right. But again, I'm new to using this too. Okay, so it looks like this cell 6 executed, and I now have a histogram. So Molly says, do I need to download Anaconda? Yes, you do, Molly. So you need Julia, and I think at least 1.14, if I remember right. But on this system right here, I've got Julia 1.15. So that would be your first step, is to install Julia. And then your next step would be to install Anaconda. So if I remember right, it's a little while ago now, I went to Julia Lang and I selected something that said Miniconda. And then I downloaded Anaconda for the appropriate system. Windows, Linux, Apple, etc. Okay, so it's not something that you can do straight away, Molly. It'll take you a little while. Okay, anyway, continuing on. So let's see if I can scroll down. All right, so next, m equals 2, n equals 2. So we're putting these two in memory. And then what we're doing is we're going to generate a random matrix. Okay, now this is done in a particular way here. So I'll explain the syntax. So what we've got is, so focus first on rand. So we've got rand round bracket m comma n. So that would generate an m by n matrix with random numbers in it from 0 to 1. Okay, but since in this example what we want is to generate a random matrix, I think, with entries between -1 and 1. Okay, so what we're doing is we're doubling those, so it makes the entries of the matrix between 0 and 2. Is that right? Or is it the other way around? Okay, anyway, so we place them between 0 and 2, and then we subtract 1. And that makes them in the range that we want. Which let's go up and have a look at the range we're meant to have those in. Okay, so entries between -1 and 1. All righty. Okay, now let me look at the chat. Okay, so Molly said, I have Julia and followed the instructions from the course website to open Jupyter, but it hasn't been working for me. I'll just ask on Piazza though. Yeah, Molly, it's really an involved process in my experience. I'm not a computer science person though, so for many it's, well, let's just say I'm not great with, anyway, I don't need to dig myself a hole. I'm good at some things. So yeah, but it'll take you a little bit. So you need to install Julia, you need to install Anaconda, and then you need to get the two to communicate. It's let's make an analogy. It's like if you go to a restaurant and the cook and the waiter don't speak the same language. So you've got to teach them to speak the same language, but it's actually a lot simpler in this case than it sounds at first. You've just got to install the right packages. So what we see here, once you install Anaconda, is you've got to basically type in these codes that are in the hints here, right? And then everything should work. Okay, so Zhang says, I think the course material is uploaded to, I think you said GitHub, and that's correct. So Yoni's got a folder in GitHub, and it's in the weeks folder on GitHub. So that's accessible through the course website, which is accessible through Blackboard. Okay. Bo says, can we get this tutorial 1 file after class? Well, Bo, you can get it right now, I think, because it's on GitHub. So you would just go through your Blackboard site, find the course website, go scroll down towards the bottom, look for something saying GitHub and follow the link. And then you'll see Yoni's handsome face there, I believe, and 4 folders, if I remember right. One of them says weeks, so you open the one that says weeks, and then you'll see one of these files, .ipynb. So that's what you want, and it's basically what we have here. So you'll need to get that downloaded on your computer, open it through Anaconda, and then make all of these commands work. So to do that, you need to, like I said earlier, write pkg.add and so on. Okay. Yep, thanks, Walla. Try to download Julia Pro. Yep, good. Okay, Zhangbai says, I think the course material is uploaded to GitHub. Yes. Yes. Okay, great. Yes, thanks for the link. Thanks very much, Yoni. That'd be great if you can help Molly. Okay, good. So let's scroll down. I think that's the chat for now. Right, so we've created a random matrix, and it's displaying that in tabular form, which is handy. Okay, next, so here we've just entered M and N, and then done the calculations straight away. Now, in cell 5, we're actually going to make this as a function. So we're building a function, and we're going to call it my_rand MAT. And so we've got the R and the M are capital, and the rest are lowercase. So we'll want to press Shift-Enter on that to define that. Okay, great. That should be in memory on my system here. So you want to do the same. And then let's try it out, and it should replicate what we did up here in line 4. But this time we've done so with a user-defined function. Okay, M not defined. What's going on here? All right, I'll try that again. Maybe I've missed loading a package up here. All right, M not defined. Okay, I don't know. Don't know, but maybe that's because I need to do using linear algebra first. I can see that this seems to work. Okay, fine. All right, now so in line 8, we're building on our histograms. So this time we've got N is 10,000, and then we're generating some data. So if I were doing this in Mathematica, I would generate the data by writing table, and then I'd write a curly bracket, J, comma 1, comma n, right? So this is sort of doing the same thing. We're tabulating with the square bracket, but we do this with the words for. So we're generating a list of data, but what is in that is the determinants of those random matrices. Okay, so these should be numbers between, well, let's see, between -2 and 2, right? At least that's what it's showing us here on the histogram. And theoretically, that should match. Okay, and so have a look at the shape of this. It's not quite a normal distribution. It's a bit different. Okay, now, so that should have been a 2 by 2 matrix that we were taking determinants of in that example. Now, if we go down here to line 9, this should be for 3 by 3s. Okay, so I need to scroll up. Okay, so here we enter above m equals 3, n equals 3, but it's done m comma n equals 3 comma 3, which is handy. So you don't have to create new lines for those. Okay, but the shape of this is a little bit, I guess, pointier. So if you compare, oh, sorry, Chris, I think I accidentally unmuted you. Anyway, okay. All right, but what I was saying is, yeah, this one's a little bit wider than the one below. And as we increase dimensions of the matrix, I think that those should get even narrower and narrower. All right, how are we all going out here in the physical audience? Okay? All right, good. You all look industrious. Okay, how are we going here on the chat? All right. So why my rand mat cannot work? I don't know. I had this working at home. But right now it just doesn't work. At least I don't think. But then again, it seems to work inside this cell 8, so I'm a little bit confused at this point. You know what, maybe I was just, yeah, maybe I accidentally deleted something, so let me just try. M comma n equals 2 comma 2. Okay, that's running. Well, there it works now. Okay, so for some reason that wasn't in memory. Anyway, guys, like I said, I'm a little bit new to this. Moving on. All right, so Xiao Fei says, I write label equals false, but my histogram still has a label. Well, in English, I think in most versions of English, label is spelled L-A-B-E-L, if I remember right. So let's have a look at that piece of code up here. Okay, yeah, have a look here. L-A-B-E-L. So that would be a command in Julia. Yep. So hopefully that works for you now. All right, moving on. Okay, so we got up to those two histograms. All right, so next what we're going to do is we're going to construct 50 by 50 matrices with random entries. Okay, but we're going to do quite a lot of these. So this involves a lot of data. So 10 to the 4th of these. All right, so let's have a look at this. For 1 to n, A equals my random matrix. And then AI is the inverse of A. But note that when the data goes in numerically, the inverse of the matrix, it's got some truncation errors in it, right? When you take the inverse of the matrix. And so you would expect then that A times A inverse, since A inverse is not exactly the inverse of A, it's just an approximation. So A inverse is, well, close to I, but not equal to I, okay? In other words, the entries in A times A inverse will be close to 0 away from the diagonal, so something like 10 to the minus 16. All right, so then if we subtract the matrix I, then we should have a matrix that contains mostly, well, entries mostly close to 0, if not all close to 0. Okay, so as we go through, what we're doing is we're appending onto the data the new matrix, or the new ERR, which is a sum of the entries of the matrix. So not quite a determinant this time. So what we're doing is we're just adding up all of the entries of the matrix, and this is called the Frobenius norm, sum of the elements of the matrix. And so we get a number there, and so we're generating a list of numbers. In fact, 10 to the 4th of those. And then what we want to do next is construct a histogram from that data. So I'll run that. And then, so that should, yeah, there's an asterisk there, so it's still going. Okay, so Rob says, how do we create I? Rob, I have a feeling that that's somehow built in, right? Because I didn't enter that. Okay, does INV function produce a pseudo inverse? Well, pseudo in one sense, but I think not in the sense of least squares and so on, right? Pseudo inverse is a tool for doing some aspects of numerical analysis, including least squares. So this inverse is just an inverse of the numerical numbers in the matrix there, right? So it's not quite exact because those are truncated numbers. Okay, all right, so I'll run the histogram part now. And that's running, but you see the cell below that. Okay, so let's scroll up and have a look at this. Oh, whoops, wrong. I think I have to shift the chat up now. Okay, so what we see here in this histogram is a great big skinny spike at 0, which is interesting, right? So yeah, that's a phenomenon of taking the Frobenius norm. Okay, so these are, we end up getting a lot close to 0, but not actually equal to 0. Okay, next, so sort. Sort is a function that does exactly what you might think. Sorts it. So here from looks like least to greatest, which can be useful. Okay, so let's just try running that. All right, so now it allows us to see what's in the data. Okay, so we can see we have a great many numbers that are close to 0, 10 to the minus 10, 10 to the minus 11, and so on. Some negative, some positive. Okay, maximum. Well, that does just what you might think. It takes the maximum out. All right, but in this case, since from the last time I ran this function, we've got different numbers in it, so I should have a different maximum now. And we see it now matches what I've got there above. So it's taking the greatest, which is still 7 times 10 to the minus 10. Okay, so pretty small. Okay. All right, try to use filter for filtering out the outliers. Okay, so I don't quite know how to do that yet in Julia, but let's just describe that process. So normally, if I were to do this in Mathematica, I would write an if something is greater than whatever, tolerance, for example, then either discard it or take note of it, and then otherwise it would do the opposite, right? So that's what I would describe as filtering the data to seek out outliers, right? So it's just putting a conditional in and then a command if that is met. Okay, so 2C, and I'll remind you of that. So in 2C, we were calculating the product of the norm of two vectors u and v, and then subtracting the absolute value of the dot product. Okay, so this is the Cauchy-Schwarz inequality, and so we see here in the comment that the Cauchy-Schwarz inequality would say that this is positive. Okay, so yeah, in particular, what we're doing is we're generating a 4x2 matrix. Uppercase N is again 10 to the 4th, and so we're iterating through those 1 to 10 to the 4th. Okay, so we make a random matrix that is 4x2, and then U is equal to A colon comma 1 with square brackets. All right, so what that is doing is it's pulling out the first column of the matrix A. Now, since it's 4x2, we only have 2 columns there. So this is the first one. And V is the second column. Okay, so once we have those in memory for the particular value or iteration, say I between 1 to n, then what we're doing is we're calculating the product of the norms, right? So that's just a scalar product. And then we're subtracting the absolute value of the transpose of U multiplied by the column vector V. Okay, so what that does is it just replicates the dot product. But here we can do it with a matrix product by transposing the U. Okay, and then again you see push exclamation data comma ERR. So what we're doing is we're appending this error onto our data at every iteration to form our data set. All right, now have I run that yet? No, I don't think so because it says in 12. So I'll run this now. Okay, it seems like it finished, but now we see the histogram below. So I'll run this now, but you can see it already. Right, so we have a histogram with an interesting shape, okay? So it's not quite symmetrical about the rectangle that meets the maximum this time, unlike the other histograms. So it has a tail that kind of fades off less rapidly on the right than it does on the left, apparently. Okay, but yeah, we're getting positive entries. Okay, let me have a look at the chat. So appears like there are no new questions in the chat, but speak out if you have any. Okay, so now that brings us to, I think it's question 3. Okay, so this comes from Yoni's book with Hayden, Statistics with Julia. Okay, so in this, they build this function. The idea here is to generate a polynomial, right? We're doing so with a function. We want to generate a polynomial, and then we want to find the roots of the polynomial, real roots of the polynomial. So as you know by the fundamental theorem of algebra, there should be n roots if we have a polynomial of degree n, but those are complex, right? So in this case, we're not taking the complex roots, we're just taking the real roots. Okay, but so what we have here is a polynomial generator. So we're building a function. We're calling it polynomial generator with a capital on the G. And you see round bracket A dot dot dot. All right, so it's like you are going to enter an array, except you don't put the front and the last bracket of the array. It just allows you to have an arbitrary number of inputs there. Right, so you don't define how many, an x and a y, for example, that are the inputs of your function here. It allows you to have more if you like, right? So when you enter that. All right, so n is the length of a minus 1. So if you think of a as an array, let's say, you know, four entries, for example, you have to accommodate the x to the 0 as well. So that's why we've got one more coefficient than the degree. So n equals length of a minus 1. All right, poly equals function of x. And we return the sum of a square bracket I plus 1 times x to the I. So we're starting with 0 so that our first term has an x to the 0. So that's the constant term. All right, and if you look at the a and the square bracket I plus 1, so you're just indexing out of that and pulling out the I plus 1th entry of your input. Okay, and that ends the function there. And then we want to return the polynomial. And then, yeah, that ends the greater function, polynomial generator. All right, so now down below that, polynomial equals polynomial generator. So here's where we are entering our coefficients, 1, 3, and minus 10. Okay, so you might want to do that by hand as well when you get the chance, just so you can see what's going in and what's coming out better. Okay, I always recommend when you're building some code to build a toy example, simple example that you can calculate by hand, so you can see how it agrees when you input that in the computer. All right, and then we find the zeros of that, or the roots of that polynomial between -10 and 10. Okay, and then looks like the last time I ran this, I had a little issue, so I opened a new cell and added 7 and 2. Anyway, we can do that again. Sure, 9. Okay, so now if you've downloaded the notebook and at the end you see that it requires pie plots. So this seems to not quite work in Julia 1.15. Okay, but on my home PC, I have Julia Pro running, and this ran totally fine. But we couldn't get the pie plot to work on this version of Julia, which is 1.5. Oh, sorry, I've been saying 1.15, but I can see now I'm reading 1.5.0. Okay, so sorry about that. All right, so I'll skip that and I'll go straight down to this. Now, when I ran this, I had to enter using PKG and do so for latex strings and measures. Okay, so you might need to do that too. All right, but let's scroll down and have a look at what we're doing before we run this. That says cell 30, but it'll be cell 16 when we run it. Okay, so we tell it the packages that we're using, and then we're defining f of x comma y. So you can see that this is just, well, the contours of this would be elliptical, right? 3x squared plus y squared. But this is a three-dimensional function. So you can think of this as a surface where the horizontal slices of this are ellipses. Okay, now you can consider vertical slices too. So a vertical slice would look like a parabola for this function. And that's what we're doing here below that. F0 of x equals f of x comma 0. So that puts y equals 0 into the original function, and so what we're looking at is just 3x squared, right? Which is, of course, a parabola, okay? Now, in the next one, f2 of x, we have f of x comma 2. So again, we're putting y equals 2 in taking a vertical slice of this surface. And so that would be 3x squared plus 4. Okay, and then we create some arrays, x vowels and y vowels. But Yoni tells me that that doesn't go into memory entirely as an array. It just pulls things out as required, which is good. Okay, then we're going to plot that and have some fancy colors here. So you can see this one's a little bit more elaborate than the things that we've run earlier. Okay, so one day you'll want to get fancy and learn how to do all of these things. Make plots with colors and so on. Okay, so let's run this. Takes a little while. You can see here I've modified it from the one that is downloaded to make this function without the, I guess you'd call it heat map. Those are the words I thought I saw in here somewhere. So there's a part in the original one that works on my home system that gives you basically an image where the colors in the image correspond to the slope of the function. Okay, so to make this work here with Julia 1.5.0, we had to remove the P3. So we have only P1, P2 there at the bottom, on the bottom line. I think there were some commands to delete, if I remember right. And we've got layout equals 1, 2. So those are the differences between what I've got here and what you might have downloaded from GitHub. Okay, but what you see here, and nicely, we've got it labeled, f of x comma 0 is the blue one, the blue parabola. So remember that was, I think, 3x squared. And then the red one, which is above that, is f of x comma 2. So these are vertical cross sections of the three-dimensional surface, which is on the right. Let's scroll over and have a look at that. Okay. So yeah, as you take vertical slices through the surface, you get those parabolas, and you can change this. So if we go up and let's try to change this, you can enter your own. So let's take f of 3. Run that again. Okay, and now you can see there's a little bit more of a gap between those two. Okay, anyway, how are we going, everyone? Great, still looking very industrious. Good to see. All right, and I don't see too many questions. Oh, yes, there's another remark in the chat. Okay, I have a question for question 2, part B. In the for loop, what does push exclamation data comma ER used for? Well, if I remember right, it's appending. So let me just, I've got 2 cheat sheets here of a lot of important Julia commands that I keep with me. In fact, they're laminated so that if I spill coffee on it, it's still okay. All right, so let me find this. Push, yeah, so try this just in a new line. So let's try it here maybe. There's a blank line. Okay, so I'm going to write push, exclamation. And round brackets, okay. So if I just put a comma 20, what that should do is append 20 onto the end of a. So I expect then that a would be an array. All right, now let's see if I can remember the syntax properly. So let's just go square bracket 1, 2, 3 and see what happens. Shift enter. Okay, so it's running. And yeah, that looks good. But what I'll note is what we have here is a column, right? So it seems that the syntax I have entered corresponds to a column, right? Whereas if I wrote something similar in Mathematica, that would be a row. And you can see that the 20 is then appended on to the end. Okay, so back to your question, Mengfei. What does push exclamation data comma air used for? Well, so in every iteration of the for loop, you are generating a new ERR, right? So a number which should be close to 0. So you're building an array, right? In each iteration, you add a new entry to the end of it. Okay. Okay, Yoni says, do question mark push to see the help of push. All right, let's try that here. Question mark space push. Exclamation. Shift enter. Okay, now we're given some functions at the beginning. Okay, so functions that are like what we typed in, and then it's telling you how it works and how to use that. So this is basically the help file. All right, so I would think that works for all of the built-in functions in Julia. Okay, but Yoni will tell me if I'm wrong. Okay, Zichuan has a question. How to generate a polynomial formula manually? All right, well, we did that up here. So I'm going to get rid of this because this takes up a lot of space here. Okay, so you want to generate a polynomial formula manually. Well, you just pull out a little bit of this code here. Okay, so let's just have a go at this. I'm going to copy this. Okay, so I've pasted that bit there, but what I need to do, let's see if we can, above that, enter a equals 1, 2, 3. Now I'm really just guessing because I'm not an expert in the syntax of Julia yet. Okay, but I've entered an array. All right, now let's think about what happens here. So I would go through 0 to n, so I need an n as well, don't I? Well, I would want n being the length of this -1, right? Which we also had up here. So it was round bracket, I believe. Okay, so I need this part. So I'll copy that. And we'll come down there. And I'll pop it in there. Okay, so n here should be equal to 2. And then I would be taking a sum, right? Indexing on the array and then multiplying it by x to the power of I as I goes from 0 to n. All right, so let's try this. Okay, x not defined. So in that case, I'm missing something. See, I'm accustomed to it having symbolic stuff built in. All right, so let's see what I'm missing. Okay, so this here suggests that, I mean, if I read this line, poly equals function of x, that's just a function of x, right? So x would be the input, but this is not symbolic, so I can't view it as a polynomial as I might do in another language that is symbolic. So it's just a function. So if you want to think about polynomials, think about them as arrays, right? Every time you have an array containing just a row, for example, you can think about a corresponding polynomial where the entries in the row are the coefficients of x to the power of position. All right, okay. But if you like free software that does symbolic things, Maxima is free. So if you just need to do some symbolic calculations and you don't want to have some paid software like Mathematica or MATLAB, Maxima is a decent one. So in fact, I'll type that here because it has an unusual spelling, like Jupiter. But Maxima, something like this. Okay, anyway, let's scroll down. All right, so there's something in the chat. Yep. Okay, just remarks about the color system. Okay, and we've finished the prac content, so I think I'll just wrap it up for now. Thanks, guys. I'm going to keep this on, the Zoom on, because we've got some new people just walked in, and we're going to do all of this over again. Okay, so thanks everyone at home for coming along and asking questions and so on. So if you want, you can stick around and hear similar content again. Up to you. Okay, but otherwise, I'll see you next time. Okay, everyone who's just walked in, welcome. So we're here for MATH7502. Anyone who was in the previous session, well, provided we don't have too many people in here, I guess you would be welcome to stay. But I do believe that new people will be coming in, and because of the dreaded illness, we want to space everyone out. So just be mindful that we need to space ourselves out, right? Okay, thanks, Yoni. Well, I don't think so, no. It's just a matter of you. I mean, if you read this, that's the best yeah. Yeah, so you gotta get the using clock. I don't know. I think you're gonna have to ask Tony because I don't remember the sequence. Make the clock. We got practice. No, this is a data science. Yeah, hi guys. So I'm now talking to the Zoom session. So if you've recently entered, so we're here for Math7502. You might have heard some background chatter. So from what I can see, according to Jonathan, so Jonathan says, hello, I think the mic is picking up all the classroom noise because it's pretty unintelligible. Yeah, so I've been out and about trying to help a couple people with loading some packages. Okay, let's see. All right, so I'll scroll back up to the top of this. All right, so here we have a 7502 prac problem set. Now, as Yoni said earlier, this is not going to be a course purely on Julia. Julia will be the tool that we use to perform linear algebra and some data science. So yeah, no need to fear, but the sooner you can learn a few skills in Julia, the better. Okay, so if you didn't hear me introduce myself before, my name is Sam Hambleton, and we've also got Walla here. So if you're in the physical class, then hopefully Walla can answer any questions you are if you're here in class. For the first couple of weeks, I'll be up here, hopefully just answering questions on the Zoom chat. Okay, and I'm just saying I get distracted, and so if you're here in the physical chat, maybe direct your questions to Walla, so I can focus here on the Zoom chat. But again, we'll see how this runs. I might find myself with a lot of spare time to answer questions both in Zoom and in the physical class. Okay, so we've got 4 problems here. The first one asks us to create a script that approximates the infinite series 1 on k squared, and that should be close to pi squared on 6, as predicted by the Riemann zeta function at 2. All right, so let's just run that. Now, since I've run these calculations earlier, you can see the output down below, but part of your task is to get these calculations to run on your machine, right? And so some will just run straight away, like what we've got here in the first cell. But others you've got to go and load packages along the way. But once you've done so, they should then work for good, which is great. Okay, so I'm going to change this so I get different numbers. So let's first try this with n equals 10. And I'll press Shift and Enter to execute that. Okay, so what I've got here is I've entered uppercase N is 10. And so what I'm going to do is calculate the sum of the first 10, 1 over the squares of the integers, and add those together. Okay, and then after that, I subtract pi squared on 6 so that I can compare this against 0, right? So in other words, if we get a number close to 0, then we could see that the sum is converging towards 0. All right, now just with n equals 10, well, we've got something like minus 1/10 as the sum, all right? So not terribly close to 0, but maybe close enough that you could believe that this is plausible, all right? So let's take n a little bit greater. So n equals 100. Shift Enter. Okay, and now you can see that the output is smaller. So this is quite a bit closer, well, the sum is quite a bit closer to pi squared on 6. Okay, so people in the previous session asked how to make the letter pi in Julia. Well, that's easy. You just put a backslash and then write pi, and then press the tab button, and right in front of you, what you had written will turn into the Greek letter pi. All right, which is handy. Okay, so now that we've got this working for 100, let's increase this. Let's go 10 to the 4th, so 10,000. So we'll take the first 10,000 terms and add those together. Shift Enter. Okay, and now you can see it's quite a bit smaller because now we have e minus 5 at the end. So that means 10 to the minus 5. So minus 9.99, etc., times 10 to the minus 5. So this is a pretty small number in distance from 0. Okay, so next, using plots. Okay, so for that to work, you have to go either in Julia. I'm using 1.5.0. So when I did this, I opened up Julia 1.5.0, which looks like a command prompt. And I just typed in, this using PKG with an uppercase P, semicolon, and then pkg.add, round bracket, plots, and I pressed enter. And then you can hopefully come back here and write using plots. Okay, so let's run that. Okay, good. Now, now that that's run, you should be able to run a histogram. Okay, so you can already see the histogram that should come out, or similar. Of course, this is made up of random numbers, so it'll be slightly different. Now, what we have is RAND, so RAND, with a 10,000 inside the brackets. So this is 10,000 random numbers, presumably between 0 and 1. Okay, and so then we put label equals false, and n bins is 50. So this is the number of rectangles. I'm fairly sure the number of blue rectangles there that we want to create. So if you increase that n bins number, then you should have more rectangles, right? So each one of these rectangles includes, well, several data points. Okay, so let's press it, shift and enter, and it ran. Let's have a look. Okay, it looks fairly similar to what we had earlier. Okay, next. So next what we want to do is create random matrices. Okay, and the way that we do this is, well, we first try this process out. We put m equals 2, n equals 2, and then we have a random m by n matrix. Okay, but this time it's just 2 by 2, and then we're multiplying that by 2 so that we increase the range. And then we're subtracting 1 from each entry. So that's why there's a dot minus there, because that is subtracting from each entry the number 1. Okay, and then we end up with the kind of random matrix that we're after. Let's try that, shift and enter. Okay, and so now we see that the entries are between -1 and 1. Which is what we want. Okay, good. All right, now next what we're going to do is build a function to do this, because we'll want to use this function again and again. Okay, so we're defining a function, myRandMat. Okay, so there's an uppercase R and an uppercase M there. But you could change the name, right? You could call this something like Tina Turner is a great singer, for example, right? Because it's you're making up the name there, okay? But we'll go back and keep the original one, so that it works throughout. Okay, so this is just applying the process that we applied above. All right, so at this point, M and N should be in memory from the previous calculation, I think. Okay, so that has now put that function into memory. And then I can scroll down. All right, let me have a look at the chat. I would like to suggest to charge your laptop before the battery dies. Well, Fadi, that's a good idea. Thanks. So I'll have to get into the bag and find the charger. Hopefully that's enough time, and then I've got to find a plug-in. So Give us a moment. Okay, so that means I've got to shift the laptop a little bit because the plugin's on the other side of the room, from what I can see. So I'll do this carefully. Okay. Still with me? Great, thanks, Jonathan and Fadi. All right, so where were we? I believe that we just entered the random matrix function. Okay, so now we'll try this out. Okay, it seems to work. Let's try it again and see if we get different numbers this time. Yep, great, it's working, and the entries are between -1 and 1. Okay, next up, we need to include the using linear algebra function because we've got a determinant calculation here. So det myrand mate. So what we're doing is just taking the determinant of these 2x2 matrices. Now, since the entries are between -1 and 1, this places the determinants between -2 and 2, right? Because the signs could all be such that you could end up with something very close to -2. And likewise, on the upper end of the spectrum, you could end up with a determinant that's very close to 2. All right, so I'll press Shift-Enter here. Okay, and that's all good. Okay, next, we are going to construct a histogram containing the determinants of a whole collection of random 2x2 matrices. So we generate an array called data, and what's in that are determinants of 2x2 matrices, and so n goes from, or say j, we're iterating as j goes from 1 to uppercase n, and that is 10 to the 5th. So from 1 to 10,000, we're creating 10,000 determinants of random matrices. And then what we're doing is we're plotting a histogram after that. Okay, now we see bins equals 100, so that's 100 rectangles. Label equals false, so no labels other than the numbers. And we're taking the histogram of that array of data. Okay, so I've got a comment from Jonathan. Is there any significance to using the underscore? Well, Jonathan, to me that just looks like just Julia's syntax. So let's just run this and then try it without, and that'll answer our question. Okay, so that ran. right? And then if I try it without, I'm guessing it just won't work, and we'll probably get an error message. Okay, Shift Enter. And it's the one above, remember? So we'll scroll up and see what happens. Okay, syntax, invalid iteration specification. So apparently it's needed, right? So we better go and put that back in. So this seems to be just the syntax of a for loop. Okay, so, and I'll just say again, Jonathan, that I say so being an expert in other software, but not this one. So I don't totally know all of the syntax of Julia at this point. Okay, so I mean, I'm learning that a little bit along the way, but I've got 2 pages of cheat sheets of important syntax and commands for running in Julia. Okay, so Fadi says, not the same as Python. Yeah, that's correct. So not the same as Python. But I mean, there are similarities, right? Okay, so now that we've put this underscore back in, works again. All right, so now in the next one, we're doing the same thing, except for, in this case, our random matrices are 3 by 3 random matrices, and we're taking the determinant of 10 to the 5th random 3 by 3 matrices. Okay, so let's just run this. All right. Good. Okay, so those 2 both run on my system. And now make an observation in the top one where you have 2 by 2 matrices, no matter how many times you run it. What you'll notice is that the shape of this histogram is different than the one below it. So what we see here is a sort of a wider base, whereas in the one with 3 by 3 matrices, we have a skinnier, more like a tower. Okay, whereas the one above it's a little bit more like a mountain, but not quite like a normal distribution. Okay, great. Let's move on. Okay, next, now we're going to do a similar exercise, but with 50 by 50 matrices, and this time we're iterating over 10 to the 4th such matrices. Okay, so we've got data equals square bracket n square bracket, and then that data is being built below in the for loop. So we have 4, 1 to n, and then what we're doing in each iteration is we're building a random matrix A, which is of course 50 by 50. And then below that, we're calculating the inverse of that random matrix A. However, note that these are just decimal numbers, okay, floating point numbers. So when you take the inverse, you don't exactly have the inverse because those decimal numbers are only approximations of some number that has a nice recipe, you know, for example, a rational number or some transcendental number or some combination of numbers, for example, an algebraic number. Okay, so the point is that the inverse is not a perfect inverse of the matrix A. It's an approximated inverse, and that comes with truncation errors. So A times A inverse is not exactly equal to the identity matrix, but it should be pretty close, right? So away from the diagonal of A times A inverse, you should have a lot of numbers that are, you know, in the size of, say, 10 to the minus 15 or something. Okay, so now when we subtract the identity matrix, what we should have is a matrix that contains entries that are all around 10 to the minus 15 or minus 16. Now, what we're doing when we calculate ERR is we're taking a sum of all of the entries in this 50 by 50 matrix. And this is called the Frobenius norm, sum of the elements of the matrix. Okay, so that goes into memory in each iteration. And then you see this fancy word below, push, exclamation. Okay, so and then in front we have data, and at the back we have ERR. So that's the matrix that we just calculated above, or the sum of the entries in that matrix. Okay, so what we're doing here is we, in each iteration starting with 1, we form an array called data, okay? And so as we go through each iteration, we include a number on the end. We append a number on the end of the data set, and these get bigger and bigger as we go through from 1 to uppercase N. All right, so that's what's going on there. Okay, so let's run this. Okay, so you can see the asterisk telling us that that's still running. So we wait. And we wait. Okay, now it says in 39, so that's finished going into memory. So now that function should work. And we should have an array of data. So let's form the histogram of that, and you can see what it's going to look like below. But it's running now, so let's scroll up and have a look at it. Okay, now what we see is a very, very sharp peak with a height somewhere around 2,500. And it seems to be centered over 0. So this is saying that most of these Frobenius norms are very close to 0, but they're probably not equal to 0. Okay, so in fact, you can see just how close they are. They're extremely close to 0, right? So you've got some entries of those matrices which are positive but small, and some which are negative but small, and so you're adding those all together. And so you'd expect to get a very small, in absolute value, number. So we have quite a few entries that are very, very close to 0. Okay, good. Okay, next we have a new function, sort. Now data is already in memory. So what sort will do is just sort the numbers in the data set from least to greatest. Okay, so we can see them all sorted, which is handy. Okay, so let's do that. And then I'll scroll up to show you the output. Now, so the very least one is still of the order 10 to the minus 10. So it's fairly small in size. And it's negative, so minus 4.05, etc., times 10 to the minus 10. So that's the least element of data. And the greatest element of data is 9.437, etc., times 10 to the minus 11. Also pretty small. Okay, good. Maximum. Okay, so maximum, obviously, we'll just take the maximum of this data set. And we can see that this should be 9.437 times 10 to the minus 11th. But here you can see it doesn't say that, and that's only because I haven't run it for this data set yet. So let's do so. And now you can see the maximum matches the maximum according to the command. Okay, next we've got a hash, so a comment. Try to use filter for filtering out outliers. Okay, so I don't quite know how to use that command. Actually, if I think about it, it's probably written there, filter, round bracket. Okay, so that gives us a hint. But if I were to construct such a function, and you might do so if you're using, I don't know, some spectral analysis, you might want to filter some data in the Fourier domain, for example, or filter out noisy parts of data. Okay, so you typically do that with an if. So if the data is greater than this, or greater in absolute value than some tolerance, then either discard it or take note of it, and otherwise do something else. So that's how I would construct such a function. But since we now see that there's probably a command called filter, let's try it. And I'll probably just get some error message, but let's have a go. Filter data. Okay, maybe Walla knows the answer to this. All right, so we're running it, and yep, it looks like I definitely get an error message. So what I would need to do then is look that function up. Okay, so let's try looking up the function. So I think how I do that, if I remember right, is I put a question and the space and the name of the function. Shift enter. And so that's running. Okay, and now we see all the documentation on that function. So let's have a look at that. So at the top, filter f, a, return a copy of collection A, removing elements for which f is false. Okay. So, all right, I would need to see an example, and we see such a thing below. Okay, so A equals 1 to 10, and then filter is odd. So the condition goes first. All right, let's just try this. So I'm going to copy this out of the help file. But hang on, let's have a look at this. So the number's 1 to 10, and I'm a little bit confused by it because it says removing elements for which f is false, but it says is odd. And then below that, we see the odd numbers. Okay, so I would have to play around with that in my spare time to fully understand that. So I'll copy this, I'll come up here, and then I'll place it in that cell. Okay, except for what I'm going to want here is data, right? Because, you know, I think I'm going to have a problem because the elements in data are not integers, they are floating point numbers. So I don't know exactly how to put my condition. And I think I would have to read further down there. So what happens if I put greater than 0? I think this is going to be wrong. So, and it looks like I'm getting an error message there. So I would have to read that, but I don't want to read it and waste everyone's time mucking around there. So that's something to do privately. All right, let's move on. So 2C, all right, so 2C, that problem was, hang on. Okay, question 2C. Okay, so in 2C, what you're doing is you're generating a 4x2 random matrix, and you're constructing an array of data, in this case, 10 to the 4 random matrices, 4x2 matrices, in which from those we're pulling out the first and second column respectively, calling those U and V. So here you can see U equals A colon, comma, 1, and we've got square brackets around that. So we're indexing, but we're pulling out the first column of the matrix A. Right, so in that, it's just in one iteration, we generate a random 4×2 matrix, and then we put into memory that U is the first column and that V is the second column. Okay, so now ERR equals norm U norm V minus absolute value of U transpose times V. So what is going on here is we're basically checking the Cauchy-Schwarz inequality, right? So we should have the norm of U times the norm of V being greater than the absolute value of the dot product of U and V. Now, here in Julia, we can compute the dot product using a matrix product by transposing U and multiplying that by the matrix V. Okay, of course, both of those are column vectors. All right, so these are meant to be, according to Cauchy-Schwarz, they're meant to be positive. Right? And then again, you see the word push, exclamation below that. So we're doing the same trick here. We're appending onto data in each iteration this presumably positive number. Okay, and then that's how we build our data set. Okay, so let's run this. Okay, and I think that's gone through. Okay, and then I'll just redo the histogram there. So histogram of the data, legend is false. Let's have a look at that. All right, so when you look at this, and since I've run it again, we see the same sort of shape, right? It's not just a coincidence, but you'll notice that it's different to these histograms up here, right? So these are centered about 0, whereas the bulk of the data in this is not, well, it's not symmetric about any given point, right? It's got a long tail on the right-hand side of roughly a half, and it drops off a bit more quickly on the left of that. Okay, so this seems to be a phenomenon of these numbers. Okay, let's move on. Okay, here Yoni says maybe need using pkg semicolon pkg dot add roots. Okay, so I found that I needed that in the first time I did this, so I had to actually uncomment that out and type that in. In other words, from using. So in other words, delete the hash maybe need and just have using pkg semicolon, and then this function below it should work. Now, so this comes out of Yoni's book with Hayden called Statistics with Julia. Okay, and so what we're doing here is we're building a function that generates polynomials. So inside the round bracket at the start, we have a and then dot, dot, dot. So the way I'm thinking of that is this allows you to sort of enter an array, except it's missing the brackets for the array when you enter that in. So in other words, your input is going to be a collection of numbers separated by commas. All right, but within this function, it's applying some indexing, right? So like we see on the, I guess, the 4th or 5th line, sum a square bracket I plus 1. So we're indexing on the input of that and pulling out the I plus 1th entry where I starts with 0. Okay, so the idea is to basically build a polynomial from an array, and then we're going to find the roots of that. So that's why you needed to include the package roots. Okay, so n is the length of a minus 1, because in a polynomial you've got a coefficient of x to the 0 right? And so if the degree of the polynomial is n, then there are n plus 1 coefficients in that polynomial. So in this case, if we have a given length of an array A, then we want to take n as the length of the array minus 1, and so that we can start with 0 in our for loop. Okay, so we're returning the sum of the coefficients times x to the power of I as I goes from 0 to n. So that constructs a polynomial there from an array, except for this is a function, so this is not symbolic. So this just builds a function of x. So that the inputs are numbers, presumably, and you're not actually returning what looks like a polynomial. So if you want to do symbolic calculations, well, you've got Mathematica. If you really like free software that does symbolic calculations, Maxima is a good one. And I've written that below in what looks like cell 19. I know it's got a Y in it, but I probably misspelled that anyway, because now that I look at it, it doesn't quite look right. But I know it's got a maxima in it. I mean a Y in it for maxima. So the Y presumably is for symbols. But maybe there are two M's. I don't know. You'll have to Google that. But the good thing about that is it's free software, so you can actually run it from a USB drive, or at least you used to be able to do that. You probably still can. Okay, so right, so have we run this? Let's just run it. Okay, so it's running here, except you might need to load the packages first. All right, now the polynomial equals polynomial generator 1, 3, minus 10. So what that is, it should be the polynomial with coefficients 1, 3, and minus 10. So you'll see that the input is not actually an array because it's got no bracket around it, but you can think of it as an array as it operates in the function. And then below that, we're finding the real roots of the polynomial between minus 10 and 10. And then we see the output there. But we should be able to change these numbers. So let's try to change this. I'll make the first one 2, and then I'll run that again. Okay, and now we get something different there. Okay. Now you'll see a little bit of pink maybe in my, hang on. All right, yeah, so a little bit of pink here, basically some error messages. So I'll note that on the system at home, on my desktop system, I'm using a different version of Julia, which was Julia Pro. And I didn't have any problem loading PyPlot there. So the next function worked okay. But here in Julia 1.5.0, it didn't quite work out for some reason. Okay, so then we went through and modified the code to see what would work in this. And it basically meant deleting the commands to make the heat map, which was just an image in which the values or the height of the function, the slope was plotted. So you'd see an image in color. Okay, but let's have a look at this. So what we have here, and this also comes from Statistics with Julia. What we're doing here, and you need to load these latex strings and measures. So what we do first is we declare that f of x and y is 3x squared plus y squared. So the contours of this three-dimensional surface would be ellipses. But we also have vertical slices that are called cross sections. So below that we have f0 of x is f of x comma when y is 0. Okay, so that should then be just say f equals 3x squared, which is a parabola. Okay, and then below that, now previously this was a 2, so I'll make it a 2 again. So this will be f2 of x is f of x comma when y is 0. Okay, and then we generate arrays, and that allows us to plot. But you can see that we're getting fancy here by including color in our plot. So color and labels. So there are a lot of commands for color and labels in there. Okay, but in the end, so here we see heat map. So that's the part that that I didn't plot there because it didn't quite work out with this Julia 1.5.0. So I removed the commands to plot that below, and I put only plot P1, P2, and I changed the layout to 1, 2 rather than 1, 2, rather than 1, 3, I think. Okay, so let's run this. And it's still running. Okay, but what we have here on the left, we have with labels, we have f of x comma 0 and f of x comma 2. So these are the two cross sections that we talked about earlier when y is equal to 0 in blue and when y is equal to 2 in red. And let's have a look at the three-dimensional surface on the right. So I think I'll need to move the chat over so you can see it. All right. And there it is. Now you can see the three-dimensional surface, but you can imagine if you took out a knife and cut through that three-dimensional surface vertically, you would get parabolas, which are those displayed on the left. If you cut through horizontally, your contours would be ellipses. Okay, and so that would have been somewhat visible in the heat map that we're not displaying here. Okay, in the last session, someone asked, what is push? You're seeing push a lot. So what is push? So you could go press question mark and then push exclamation, round bracket, and then press shift and enter, and that would pull up the help file on push, and it would tell you all about push. But I find it easy to learn with a few examples. So in my laminated notes on several important commands in Julia, I've got that push is basically appending a number onto an array. And here I have an example in the cell labeled 22 below. Push exclamation, round bracket, and then the first entry there is an array, just 1, 2, 3, and then comma 20. So what I'm doing is I'm just appending 20 onto the array 1, 2, 3. But you'll notice this is a column vector. Whereas if you did this in Mathematica, you'd be looking at a row, right? So the syntax is different as it is in most programming languages. Somewhat different, but it all rhymes. Okay, I think that's all we have. So let's just scroll down and see if there's anything more here. All right, so this down below what I've got here, I've got some error here, but what I was trying to do is build a polynomial, because someone had asked in the last session, how do you just plain build a polynomial? Well, what we had above is a function, basically. So it had an input of x, and it returned what the polynomial would return. Okay, but it's not actually symbolic. It's just a numerical function. So this, as far as I understand, the software doesn't do, it doesn't return symbolic calculations or do symbolic calculations. It's all input numbers or arrays or matrices and output numbers, arrays, matrices, and so on. Whereas other software has different goals. Okay, any questions from anyone in the chat? Just let us know. Okay, I can see we've got Walla, Fadi, Kayla, Jonathan, probably a few more people. That's all I'm seeing on my screen for now. So thanks for coming, everyone. And please continue to ask questions in the chat because it clarifies what hasn't been explained yet or what hasn't been clear. Now, it is a bit of a challenge to get Jupiter and Julia to communicate. So all the best with that. Basically, in my experience in doing this in the last couple of days, you basically have to take a look at those hints that are given throughout. For example, up here, let's see if we have a hint up here. Yeah, for example, this, where Yoni says maybe need using pkg semicolon pkg.add. So I did that through Julia itself. So I opened up Julia, and then I typed the relevant commands into there, and then in here I had to say that I was using the particular thing. All right, so that does take a little while. It's a little bit frustrating, but after that, hopefully things are easy. Okay. Anyway, everyone. So thanks very much. I'm gonna wrap it up here unless you have any questions. Okay, Kayla's got a remark. She says, thanks, Kayla. So honestly, I'm very lost as I have not done much programming before. Do you recommend running through everything again on my own from this tute, or any advice? Okay, so first thing I'll say, Kayla, is that this course is not a Julia course, even though today we basically only did Julia. So much of this course, and I speak from having worked with Yoni before on this course. So it's a linear algebra course. So most of it is you're doing maths, but occasionally in your assignments you'll be asked to do some calculations in Julia. I would estimate, right? Because that's the way things worked last time I did this. So it's good if you can learn a few Julia skills, right? So the main point of today would be for you to pick up a few things, but your next remark or question is, do you recommend running through everything again on my own from the tute? Well, yeah, I mean, if you think that that's helpful, then that's probably a good idea. So, I mean, the main thing is, can you get all of these things to look the same as they do on my screen here, right? And think a little bit about the syntax. I would recommend, as someone who does a fair bit of programming, not in Julia, but in other stuff, is to write down the code on paper and pen as well. And in another color, say if you're writing in blue or in black, what the actual syntax is, write some notes in another color next to that to say what that kind of syntax does. Right, that's a handy way to learn, or in my experience, a useful way to learn a new programming language. And if you haven't done any programming before, then that'd probably be an even better idea. Okay, but I'm sorry, Kayla, you're a little bit lost. That's not so surprising. I mean, it's a different language, right? Programming. So I wouldn't feel bad about that. So you've got all semester to get better at running this. All right, so some other remarks. So there's a thank you too. Fadi says, is this explained in the lecture? I signed up myself in this class recently. Well, some things will be explained in the lecture. I know Yoni's a big fan of Julia, so I reckon he'll probably want to take a few opportunities to talk about Julia and how it runs in his lectures, but that's only a guess. All right, thanks a lot, really helps. MATLAB 10 years ago. Yeah, it's a bit different to MATLAB, but I think, at least it's free. Thanks, though. It really helps to know not to worry too much. Yeah, don't worry too much. Don't stress. I mean, you'll have some problems in your assignments where you might just struggle to understand what's being asked of you. So Walla and I will hopefully be able to tell you what those questions are asking you, and that could be some of the biggest challenge. And then usually what happens is people, once they understand what the question is asking them, they're good to go. And yeah, okay, so I'm not going to say your name right. Jean Liu. Sorry about that. I feel a little confused about the difference between V1 star V2 and V1 dash star V2. Okay, so in order to do a dot product, you have to, in order to do it with a matrix calculation, you will need to transpose the matrix on the left first, and then multiply the two matrices, right? Which are just column vectors. But if you transpose the one on the left, it becomes a row. Then you're multiplying a row times a column, and that in turn adds up the product of the entries, and you get the dot product, right? But what you have written on the left is V1 star V2. So depending on the syntax, and I don't quite remember in code, sometimes that could be a matrix product, or it could be a product of the entries and return a vector. But one good way to find out is for you to just input two vectors, V1 and V2, try both of those things and see what the output looks like. Okay, and that will quickly answer your question on that. All right, guys, it's 2 minutes to the end of the hour. Fadi says thanks. Thank you, Fadi. I'm glad you showed up and asked questions and commented. That's great. So thanks, everyone. So I think that's it, unless you have any last remarks. Okay, thanks, Jonathan. I'll see you guys next time. So I'll go ahead and sign out then, okay? Good night, everyone. Or good day if you're somewhere on the other side of the globe. See ya.